right. So you need to remember what we talked about when we were here last about valence bond theory. So valence bond theory talks about basically those two atoms reaching out their, each reaching out an atomic orbital and creating yet another orbital. It's called a bond orbital, where a pair of electrons can hang out. And those pair of electrons are shared. I just think it is so, like, poetic. I just think it's wonderful. And just like we saw with water, you know, the oxygen sharing a pair of electrons with the hydrogen, in that case, the oxygen got a complete octet. And so in tomorrow's lab, you're going to be drawing structures like water. In fact, I think water might be one of the structures you're going to draw. Okay? So we're continuing with talking about covalent bonds. Now, there's this thing called valence shell electron pair repulsion theory, and I just love it when it like all really means something. Like, well, it doesn't mean this, but in around Christmas time, where I was from, Mediapolis, we used to do this called Vespers. I don't know really what it was, but it was just kind of a nice time to go sing Christmas music. And that's what I would think of this, but this isn't really Vesper. It's, yeah, kind of something like that. Valence shell, we know what valence shell electrons are, right? Actually, we've been talking about them when we talked about a pot of valence electrons to put around a Lewis structure. Valence shell electron, electron pair. We've been talking about they come in pairs, you know, whether they're a lone pair electron or basically hanging out as two electrons that are part of either a primary sigma bond or a secondary pi bond, right? They come in pairs. The repulsion part of it, it's exciting. It's all exciting. But the repulsion part of it, actually, this is what gives our atoms shape. Okay? And whether you stay in chemistry, you know, I don't know if you will stay in chemistry. I hope you do, kind of dabble. But whether you stay in chemistry, what you'll see is that shape matters. You know, when people go to make these designer molecules and say they're trying to make a perfume that will interact with our, you know, physiology, shape matters as to how our physiology will or won't handle it. Okay, so the repulsion that's going on at the level of the atom, this repulsion actually gives shape to the overall molecule that atom's in. It's wonderful. I don't know if I'm convincing you, but it is. Okay. So again, remember what we talked about in Monday's lecture. We talked about two types of covalent bonds, covalent chemical bonds, where electrons are shared. We talked about the sigma bond, sigma, right? That's the primary bond, okay? So according to this valence shell electron pair repulsion theory, those sigma bonds, any sigma bond that's extending from an atom, and any lone pair electrons also associated with that atom, okay, are going to repulse, that gives the shape, as far apart as possible from that atom. So basically, and I'll give you kind of the precursors to what we're in for. Okay, if I were just to kind of pick, let's make it all just kind of little stemmy things. Oh, here's some things. Okay, I'm going to pick that. This is going to be an atom of interest. Okay, a really common shape is this one. This is a really common shape. I don't know if you can tell it, but I've got 4 stemmy things extending from that black ball. Okay, valence shell electron pair repulsion theory. So sigma bonds, if these are sigma bonds and or lone pair electrons, they are going to kind of orient themselves this way. That's the shape I'm talking about. Actually, here in a minute, I'm going to call that a tetrahedral shape. Okay, but that's what I mean. But it's only sigma bonds and lone pair electrons. But the other thing we talked about, we talked about on Wednesday, or this is Wednesday, we talked about on Monday. The other thing we talked about were pi bonds. And just to kind of remind you those, let's pull up our hot dog. Okay, this is C2H2, right? We said the gray things are sigma bonds, and what are the pink and purple?
The pi bond.
They are the pi bonds, exactly. So here's the deal. When we're talking about shape, and this is shape around an atom, this is one of the things that students struggle with. They want to go straight to the molecule. You want to go to the C2H2, but we're not. We're going to an atom. If I were to focus on that atom there, Let me show you. It's got, you can see it's got one sigma bond to the carbon, and it's got one sigma bond to a hydrogen. Just bare bones, let me show you what this looks like. Because the shape I'm talking about, I'm going to call it electron pair geometry, structural geometry. This shape only has to do with an atom, and what you do, that could be the sigma bond hydrogen, this could be the sigma bond carbon, around one of those carbon atoms. We say the shape around either one of those carbon atoms because they're symmetrical. The shape around that carbon atom is a hot dog. No. The shape around that carbon atom is what we say linear. Why? Because we're focusing on the sigma bond, sigma bond. Okay, and that's the real deal. Okay, so it's basically shape around an atom. The old shell electron pair repulsion theory. This emphasizes that if you're after shape, which we're going to emphasize tomorrow, and on your test you're going to have to tell me shape around an atom. If you're after shape, you ignore the pink and purple. Pink and purple, who cares? The pi bond, right? I mean, it's there to give it an octet, blah, blah, blah. Okay, but they're secondary bonds. All right. So here's where, and I know this is not about like biology or anything like that, but in biology, if you make a hybrid bird, or if you make a hybrid pea, okay, basically what you've done is to get that child, you've gone back here and said, I want characteristics of these two parents, okay, and I put them together and I get this, right? That's forming a hybrid. Well, here's the deal. These, oh yeah, this works, okay. What happens with atoms, it is so exciting. Because we said that atoms have electrons, obviously. We talked about those electrons being in different homes, right? We talked about the different types of orbitals, the S-type orbital, 1 box, the P-type orbital, 3 boxes, the D-type, 5, the F-type, 7. Okay, so those are where electrons can hang out. This is so cool. So what atoms do is take 2 or 3 or 4 or sometimes even 5 of their atomic orbitals, okay, behind the scenes, and they, if I could be a magician, they hybridize them, okay? They hybridize their atomic orbitals, and they spit out these hybridized orbitals, they're still atomic orbitals, that can go ahead and overlap and participate in, the only thing they participate, though, in is sigma bonds and lone pair electrons, those hybridized orbitals. Hybridized orbitals, hybridized atomic orbitals. Now, I do a lot of things kind of just to kind of tell you why it is. So on the test, I'm probably not going to ask you how this necessarily works, but this is how this works. I'm kind of giving you the surface of how it works. So those hybridized atomic orbitals that the atom has kind of put together some of its atomic orbitals, spit them out, okay? They are equal, which is awesome because there's some S, some P. Actually, sometimes they can throw some D in there of their own D atomic orbitals. Okay, but notice that those hybridized orbitals, what doesn't get to hang out in hybridized orbitals are a pair of electrons that are hanging out, are what we call a pi bond, pi covalent bond. Okay. So again, just to kind of, your textbook, I think, and I understand why, but they kind of talk about the shape of a molecule, and we're not even going to go there this semester, I don't think. I just want what I call the structural geometry. I know it sounds like a molecule, right? But it's not. The structural geometry is the geometry around an atom. Structural geometry or electron pair geometry. And the thing that kind of throws us off is sometimes, I'll just go ahead and show you why this throws us all off. On Monday, I told you that in a water molecule on Monday, I told you in order for the middle oxygen atom to get a complete octet, okay, we talked about, what are these? What are these around a water molecule? What are the little horn things?
The lone pairs.
They are the lone pair electrons, exactly. So the thing is, a water molecule looks like this. And again, when I ask about structure, I'm not asking about the molecule. I'm going to have to tell you which atom I want to know structure about. This is where I need to convince you that that structure around that oxygen atom is actually tetrahedral. There's actually 4 things. Lone pair, sigma bond, sigma bond. Okay. So here's the deal, and I'll kind of reinforce what this is. On Monday, we did a lot of stuff on Monday, didn't we? On Monday, we talked about 3 hydrocarbons. Okay, let's see. We talked about this one. Oops. Better leave room for, okay, where I'm not going to put the end of the dashes. I'm going to be lazy, but those are all hydrogens. We talked about this one. And last but not least, the hot dog one. We talked about this one. Okay, where at the end of those dashes, there are hydrogens. So I think your textbook talks about electron pair groups. And actually, like the slide says, right there, it's got 1 sigma. You would tell me the first to arrive was a sigma, and you tell me the second one was icing on the cake or pi. Okay, triple bond, 1 sigma, and 2 pi. 2 pi bonds, right? So the point here is that as I'm drawing these red circles, those are both just 1 electron pair group. So, all right. This actually, at the top of this slide, you might want to put a star. And so tomorrow you'll be using this information on this slide. If you hear me talk about row 1, row 2, row 3, this is the slide I'm talking about. And it's very helpful. The first column basically says how many sigma bonds and lone pair electrons do you have extending from that atom you're trying to tell the geometry about. How many? Count them. So like we said here we got 2, right? Okay, things extending from that atom of interest. We said here we've got 4, and you can see the 4 at the bottom there. And let me go ahead and make a 3. I have to find the right one here. So this is 4. And that's as far apart as they can get. The last one, it's kind of got this specific, this will work. Looks like this. 3, the middle one. 1, and if they want to get far apart, and actually I like your textbook has these with balloons coming up here. 2, and this could either be a sigma bond or lone pair electron, but it cannot be a pi bond. 3. Okay, here we go. Oops. 2, wait, yeah, 2, 3, 4. Fine. All right. So again, what are we counting? We are counting sigma bonds and lone pair electrons. Pi bonds, they're important. They give octets, but they don't give shape. So here behind the scenes is what these atoms have done. So in this case, it has taken one of its atomic s orbitals and one of its atomic p orbitals, and has combined them together and spit out 2 equal sp hybridized orbitals. That's how we say it. Okay. And the cool thing is if you want to know how many hybridized orbitals they get, all you got to do is count up how many of its atomic orbitals it combined. So it had one of these and one of these, so it got 2. In the second case, in this case right here, with 3 hybridized orbitals, okay, participating in sigma bonds or lone pair electrons, okay, it has taken one of its s and 2 of its p. 1 plus 2 is 3. Okay. And last but not least, this atom right here has taken one of its s and 3 of its p atomic orbitals, hybridized them together, and spit back 4. So 1 plus 3 is 4. Okay, so that's the hybridization going on behind the screen. So I've been kind of alluding to these, and even though I'm going to describe 2 more geometries that basically what that atom has done is kind of sprinkled a d, one of its d atomic orbitals, sp3d and sp3d2, but we're not going to worry about those. These are the 3 that we're going to work on tomorrow. I'm going to hold you accountable for the test. So the shape around this atom, this blue atom, is linear. The shape around this green atom, trigonal planar, otherwise called triagonal planar. Okay, and the shape around this atom is tetrahedral. Again, how do we know? Somebody gives you a structure or you draw a structure and you count what that first column says. You count sigma bonds and lone pair electrons. It's that easy. And sometimes you just need to put your finger on the atom of interest. Okay?
Can you say the last one more time?
Tetrahedral. So if we were to go ahead and assuming that these are maybe sigma bonds, okay, and there's an atom at the end of each one of these, we could actually come up with, this would be a sigma bond if I had atom here and atom here, a pair of sigma bonds. This would be an angle of 180, right? This would, if this is connected to 3 other atoms, this bond angle here is 120, okay? And this bond angle here is 109.5 tetrahedral. So this is kind of how if somebody gives you a piece of paper with a Lewis structure on it, you're like, you can lift it up and you're like, oh, well that's the geometry around each atom, and then you take these individual atomic geometries and put them together to make the molecule, to get molecular geometry. All right, so figure from your textbook. Okay, the first row is got 2. Okay, so it's kind of similar to what our table was before. The 2 means that it's got 2 hybridized orbitals. We're talking sp orbital hybridization. Those hybridized orbitals could be sigma bonds or lone pair electrons. The shape is linear, and there's an example, CO2. The next 2 has undergone what? sp2 orbital hybridization. Why? Because I have a 3 there. That's this sort of deal. And then this one has the 4 means that you have, if you have 4 equal hybridized orbitals, you're talking about what? sp3, right? Again, if you get lost, just kind of add the superscripts together and backtrack to your 4, sp3. Reverse engineering. I gotta stop using that term. Okay. So I've just got some figures to kind of reinforce what we've been talking about. There at the middle of, well, anyway, you can kind of see this is SP, SP2, and SP3. Linear, trigonoplanar, tetrahedral. Is it molecular shape? No. Might it be the molecular shape? Maybe. Are we going to talk about molecular shape right now? No. But it's an atom. And my point is going to be that actually water's a good example. With water, it looks like this. Okay? The shape around the oxygen atom is tetrahedral. Okay? The shape around the oxygen, this is H2O. Tetrahedral. How do you know that? Draw the Lewis structure and see the 2 pairs of lone pair electrons up there. It is warm in here, isn't it? Whew. Open another window, I think. Okay, so, because I don't know if your book emphasizes them as much as I will, but this is SP, SP2, oops, SP3. Okay. So we talked about expanded valences. I don't know if you remember, but I said I mentioned them, and actually they're quite possible because anything that is below period 3, which is a lot of the periodic table, period 4 begins with potassium. Anything below period 3, actually, you can have something that's more than an octet. Okay, and with that possibility, we have these other 2 situations in which an atom in the middle that's going to bond or have lone pair electrons can take more than 4 of its atomic orbitals, hybridize them, and spit stuff out. So we left off with sp3, so having 4 things, right? 5 things would be sp3d. 6 things would be sp3d2. So these are with expanded valences. sp3d, sp3d2, expanded valences. So let me go ahead and just kind of finish that thought with the expanded valences. Instead of, I'll put it this way, these guys would have an octet, which we're most familiar with. Okay, 8 electrons around an atom in its final Lewis structure. I'll put the number 5 here and the number 6 here. Actually, these guys have 10 electrons in its final Lewis structure, and these guys will have 12 electrons in their final Lewis structure, which gets really exciting. But when those electron domains go to skirt away from that atom that has hybridized its orbitals, okay, you get this cool thing. It's trigonal bipyramidal. In the case where you have 6 things trying to repulse away from that atom, you get something called octahedral. So, all right. But the first 3 are really what I want to focus on. So again, with the balloons, you can't have too many balloons. So linear, trigonal planar, tetrahedral. SP, SP2, SP3, and then that's at the top, isn't it? I guess the other thing that was on that table that I had you put a star next to is I told you this is 180, assuming that they're covalent bonds and they're bonded actually to the same thing. The bond angle here we said was 120. For trigonal planar, the bond here is 109.5, which I used to say that I bet that would be a great radio station, but somebody said, you know what, the FM dial doesn't go that high. So I'm like, oh, okay, guess not. So the bond angles are here. Bond angle, bond angle, bond angle. Cool. Not too bad. But don't forget, what you count are you count sigma bonds at the top of that column, that first column, I had you put a star, and lone pair electrons. That's it. Again, with the little figures here, kind of from left to right. The first 3 are what we're going to focus on, and I'll hold you responsible for. SP, SP2, SP3, linear, trigonal planar, and tetrahedral. The others are expanded valences. Valence shell electron pair repulsion theory. It's got a ring to it. I think someone should make a song to go with that. Extra credit? So I think that ammonia, not to be confused with ammonium, I know, this drives me nuts, in the same unit of material, we've talked about the polyatomic ion NH4+, right? And then there's this neutral molecule, ammonia. So ammonia, the Lewis structure looks like this. This is the Lewis structure. The pod of valence electrons have been distributed. You can see that nitrogen atom has 8 electrons around it, right? 2, 4, 6, 8. The hydrogens each have 2 electrons, so like helium. So now, we're going to answer these questions. Actually, in your lab tomorrow, you'll be answering these questions too, about the nitrogen atom. These questions about the nitrogen atom, because I said when I'm asking about structure, I'm just asking about structure around an atom, not the molecule. So the nitrogen atom, here it already says if you take 3 plus 1, no, 3 plus 1, okay, is 4. So this is where I say, go back where I said put a star and go back to that 3rd row where it says 4 at the front, and all that information goes here. That's it. Okay, so go back where I said put a star and go where it says has 4. So it's like the third row. Okay, so where it says like number of sigma bonds and lone pair of electrons is the first column. So 2, 3, and 4. Yep. Yep. So 4. What page is it?
Page 1, first page.
First page.
Last one.
Okay. And fill in. So what's its orbital hybridization? Nitrogen atom. SP3. Very good. Ding, ding, ding. What's its structural geometry? Tetrahedral. You got it. And what's its bond angle? That's it. And you can see approximate 109.5, and I'll kind of explain why that is. 109.5 would do you. That's it. Let's do the same thing for this one. Okay, I'm going to draw, in tomorrow's lab, you're going to be looking about the atom in the center. So that would be the carbon atom. So like the heading says, if you count sigma bonds, we have 1, 2, 3. Remember the pi bond, there's only one sigma, the others, or sorry, the double bond. The double bond there, one is sigma and one is pi. Okay, so that's why this says around the carbon atom we have 3 sigma bonds. Right? So now on that table, we're going to go on the second row, right? Where it starts with 3. So what's its orbital hybridization? sp2. Structural geometry? Exactly. Trigonal planar. And what's its bond angle? 120. Now this is a really good example. I mean, usually for Lewis structures we're into like right angles, okay? So that doesn't look, this doesn't really look like this, does it? But this is right, okay? According to the repulsion that would go all around that carbon atom. Valence share electron pair repulsion theory. All right. So this just kind of emphasizes what you guys just told me. Again, we're focusing on an atom, not the full molecule. Let's do this one, and let's look at the chlorine atom. So, like this slide says, around the chlorine atom, you see there's 1 sigma bond to the oxygen. I usually hold up 2 hands. There's 1 sigma bond to the oxygen atom. There are 3 pairs of lone pair electrons. So 1 plus 3 is, yeah, you're back to 4 again. So you're back to that 3rd row. So what's this orbital hybridization? sp3, perfect. Structural geometry? Tetrahedral. Now this is where I say not applicable, but you would say 109.5. I would. 109.5, but the reason it's not applicable is because there's not another thing it's connected to. It's just it's connected once with a sigma bond, and the other electron domains that are created by the sp3 orbital hybridization, the other 3 are doing this. They basically create geometry, but they're not connected to anything. So there's no vertex really. Very good. Okay, kind of a symmetrical sort of deal. Pick a carbon atom, any carbon atom. Count your sigma bonds. 3 sigma bonds, very good. So you're back to that middle row, right? That has 3. So what's its orbital hybridization? sp2, perfect. Structural geometry?
Trigonal planar.
Trigonal planar. Bond angle? 120. Okay. They're kind of fun, especially if somebody draws a Lewis structure for you. So on your test, I'm going to draw a Lewis structure, and I'm going to ask you, I'm going to point to particular atoms and ask you those questions, these 3 questions. Okay, pick a carbon atom. How many sigma bonds? 2, very good. Because remember, with a triple bond like that, there's only 1 sigma bond, and the other 2 are pi, exactly. So we're going to go with that top row. So what's its orbital hybridization? sp. Structural geometry? Linear. It's the hot dog, right? And bond angle? 180. Very good. All right. So these, and let's see how quickly I can make these. Maybe not. We said this is water, right? Let me go ahead and make ammonia. We have, this is not carbon, or excuse me, this is an oxygen. Now this is nitrogen. Ammonia looks like this. ammonia. And last but not least, methane. I'll pick this. I think we're going to go with, if you're okay with this, instead of white for hydrogen, which is usually what we do. Remember tomorrow's lab, I'm cool with any color you want to go with, is anything. The little boxes you get, they'll be different than this. They will have a code, but you don't have to follow the code. All right, so this is CH4. So for water, we have 2 pairs of lone pair electrons around the oxygen. For ammonia, we have 1 pair of lone pair electrons around the nitrogen. And for methane, we just have carbon there, and it's singly bonded to 4 hydrogens. In all of these, you guys would tell me to use that bottom row, right? Yeah. You guys would say 109.5, which would be totally right. But here's the deal, and I'll just kind of do it before I show you my slides. Anytime you have lone pair electrons like this, they actually take up a little extra room, okay? So you're going to see that actually these electrons, lone pair electrons up here, there's 4 electrons right here, 2 here, 2 here. They're actually going to squish this. So actually this bond angle is going to be less than 109.5. Okay. For ammonia, it's not as severe. Okay, ammonia is not as severe as this one. Okay, so actually this is going to be closer to 109.5, and this one will be 109. So that's why I use the word approximately. Okay. So starting with the methane, anytime you have like equal things that are connected to the atom of interest like this, it's going to follow the rule that you expect. Anytime you change it up by having lone pair electrons or something else substituted, it's going to be different. So methane, okay, ammonia. Notice, I guess the bond angle isn't given, but I think it's given coming up. Okay, so methane is 109.5, ammonia less 107, water even less than that, 105. All right, so let's do this one. This would be like a structure I would give you on your test. I've got 4 atoms of interest, and around each atom, we're going to answer 2 questions. This slide, what is the structural geometry? So I think I go counterclockwise. I think the order that the arrows were added just a minute ago. So for this first carbon here on the left, notice if you were, how many sigma bonds around that carbon? I'm thinking 4. I got you. How many lone pair electrons? None. So you're going for that bottom row, right? So structural geometry, so it'd be sp3 orbital hybridized. Structural geometry that goes with that is tetrahedral, exactly. That's how you answer that. I think we're over here to this nitrogen, okay? So this nitrogen over here, it's got a triple bond carbon, and nitrogen has lone pair electrons here. So of this triple bond, how many sigma bonds? Just 1, that's right, 1 sigma bond there. How many pairs of lone pair electrons? 1. So 1 plus 1 is 2, right. So the shape would be linear, perfect. You got it. Now going up to that other carbon, so this carbon right here, it's got a carbon double bond carbon, and it's singly bonded to another carbon, and singly bonded to a hydrogen. How many sigma bonds? 3. How many lone pair electrons? 0, so you're at that middle. So what's the shape? I'm liking it, trigonoplanar, perfect. And last but not least, we have that oxygen. So how many sigma bonds extending from that oxygen? 1, very good. How many pairs of lone pair electrons? 2. 1 plus 2 is 3. You're at that middle row. So what's the shape?
Trigonoplanar.
It's also trigonoplanar. Does that work for you? And then this one is the same deal, but I'm going to kind of from left to right, I'm going to talk about those bond angles. So actually, earlier you told me around this carbon atom, the geometry is tetrahedral around this carbon atom. So what's the bond angle? 109.5, exactly. Now we didn't do that second carbon there, but take a look at that, or we did do that carbon.
Mhm.
I thought
Yeah,
we
that
did.
goes to the
I thought we
oxygen.
did this carbon.
Oh, yeah, because we did the,
Maybe they're talking about, because we technically clicked on the oxygen,
And
but
the
maybe,
oxygen,
maybe it's saying the oxygen
I
to that carbon.
So just for kicks, go ahead and tell me, if I put a star here next to that carbon atom, tell me what sort of shape we have around it. So how many sigma bonds? 3. Yep. How many lone pair electrons? None. So on the count of 3, what's the shape? 1, 2, 3. Yeah, it's hard to spit out in a trigonoplanar. Yes. So it's trigonoplanar. So what's the bond angle? 120. 120. Yep, exactly. See, so to me, there's a lot of things in chemistry where you just gotta, physical science, you just gotta kind of think through it. I mean, mull it over, kick it around. Okay, and I don't think we did that carbon atom either. We did the nitrogen atom.
Mm-hmm.
So if I put a star here, yeah, I heard somebody say linear. Very good. If I put a star there, you guys would tell me I have 2 sigma bonds, no lone pair electrons. So it's sp orbital hybridized, so we're back to linear. So the bond angle is 180, exactly, half a circle. I'm liking it. So yeah, we just keep piling on. There's nothing going to be due. We are going to go on to the next part right quick. But this won't be due until you come back from your weekend. All right? I'll be sure, and Friday, or I'll be sure to give you my contact information.
Because we have this one and the other one that's all
Right.
in the lab.
Yep. So let's take a look at the next part right quick. Parts is parts. This is good to get this kind of under our belt a little bit because this will help with tomorrow's lab. Tomorrow's lab's looking really good. Okay. So I want you to remember when I talked about the pot of valence electrons, I even added pot O electrons, like pot of luck, pot of valence electrons. So you could be asked in tomorrow's lab or on your test to draw the Lewis structure of something that has the formula of HCO2 with a negative charge. Remember, you're going to have a periodic table, and your first step, and actually in tomorrow's lab, we're going to do some Lewis structures together, and then I'm going to turn you loose and you do your own Lewis structures. But you would go to your periodic table, or you would recognize that that one hydrogen atom will bring to the table, oh, let me go back. That one hydrogen atom will bring to the table one valence electron, so that's one electron, okay? Carbon, there's one of them, and it's group number 4. Oxygen, there are 2 of them, and they are group number 6. So this thing in parentheses is the number of valence electrons, okay? And you get that from the group number. All right? So that's that. Now, the fact that it has a -1 charge, actually, it has 1 extra electron. Okay? If it was a positive polyatomic cation, you'd have to take 1 electron away. If it was a -2, what would you do? Add 2 electrons, exactly. Okay, so this is our pot of valence electrons. Cool. And they need to find homes on your final Lewis structure. So the thing, actually, if you look at your instructions for drawing a Lewis structure in tomorrow's lab, the thing you're going to do is you're going to put something in the middle, and the thing that goes in the middle has the lowest electronegativity. Lowest electronegativity in the middle. In the middle. Okay? And here's the deal. Hydrogen never wants to be in the middle. never in the middle. Never, ever, ever. Because it's so simple, it just doesn't want to do that. So your choices are carbon and oxygen, and if you're like me, to know which one has the lowest electronegativity, you need to have a periodic table handy. So your periodic table has, they're both in the same period. We have carbon here, nitrogen and oxygen, okay? And we said electronegativity increases as you go this way. Did we say that? Yeah. Okay, so actually that, in a nutshell, is why carbon is in the center. Okay? Oops, I drove wavelength instead of electronegativity. All right. Step 1. Now, notice that on our preliminary structure, the previous slide, it had 3 sigma bonds. Okay, so you had put carbon in the middle. You had sigma bond oxygen, and sigma bond hydrogen. So it had 3 sigma bonds. So 3 sigma bonds is 6 electrons. Now our pot was 18. So 18 minus 6 is 12. So we have 12 electrons left. We got to use them. And then your instructions are going to be to take those remaining 12 electrons and to distribute them first on outside, I'll call them outside atoms. Instead of outside, actually, I use the word terminal. Terminal or outside atoms. So we had 12 remaining, and so our terminal atoms, actually we have 3 terminal atoms. 3, I think we have hydrogen, oxygen terminal atoms. But hydrogen doesn't want any more. Hydrogen stops at 2. Okay? Hydrogen stops at 2 electrons. So that's why, basically, if you count up these lone pair electrons, let's count them. 2, 4, 6, 8, 10, 12. That's those 12 remaining electrons. And why did we do that? We did that to go ahead and give these oxygens, these oxygens now have a complete octet. So your instructions will be distribute the remaining electrons around terminal atoms to give them a complete octet. And remember that hydrogen does not want an octet, it wants a duet like helium. And that's it. Okay? Well, almost. Does carbon have a complete octet yet? No. And actually, in the way tomorrow's lab goes, how many atoms, how many electrons does carbon have? It only has 6 electrons, right? So it's not done yet. This actually is going to be step number 6. Step number 5. Step number 5 in tomorrow's exercises is if your middle atom, which is carbon, does not have a complete octet, then you have to swing a pair of 2 lone pair electrons in from one of those atoms that are terminal atoms, lone pair electrons, and you have to basically convert those into a pi bond. So we have all sorts of choices here. Okay, and actually that's the point of this. It's something called resonance structures. I could bring these in, okay? So that last step, step number 5, I could do that, okay? Turn it into a pi bond, okay? And does the oxygen still have 8? Yep. Does the carbon now have 8? Yep. It's called swinging lone pair electrons in. Or I could swing it from the north oxygen instead of east oxygen. So notice I chose the north oxygen, okay? So if you compare that structure with this structure, what I've done is 2 things. But one is instead of 3 pairs of lone pair electrons around this north oxygen, it only has 2, and that 1 pair of lone pair electrons has been swung in to make a secondary bond, a pi bond. Okay, and now, what's that?
I said carbon's still hungry, he wants pie.
That's right, carbon was still hungry, he wanted some pie. Exactly. And everybody's still got a complete octet. Notice the other thing, if you do have something charged like this, you have to put it in brackets, your whole Lewis structure in brackets, and put the charge outside. Okay, that is actually worth 1 point. On your test, you'll be making your own Lewis structures. They'll be worth 3 points apiece. I've done this for some. Okay, yep. They almost grade themselves. Okay, so you swing lone pair electrons in, and we said we could have done it from either oxygen. And, you know, if we call that oxygen A, kind of the north oxygen, and call the east oxygen oxygen B, right? You know, both of them are great. And what you have, and I think I have a picture coming up of this formate, Lewis structures of this ion. But what you have are a pair of structures that are awesome, and they're both great. Those are resonance structures. Okay, how did they differ? They differ by where your double bond is and where your lone pair electrons are. So, resonance structures. Actually, I'm going to let you fill these in, but I have just a handful of slides. I'm going to, instead of starting on part 9 on Friday, I'm going to kind of finish this up on Friday. But on Friday, we'll also bring your calculators, like I said, because we're going to start in on some math stuff on Friday. Okay? So that should do it. Let's go to the Opus Art test. Actually, I think tomorrow for lab, I think tomorrow's lab, that makes more sense. I'm going to knock out these last slides for tomorrow's lab. So bring these if you want to. So bring your lecture. So we should be in good shape for tomorrow's lab.
And the dragon unicorn.